I've known Pete for a few years, and he has been kind enough to speak at a number of our events in the past, including at the past Embedded Vision Summit the past couple of years. And that's why I'm very excited that he's agreed to speak here today. Pete is an expert in image processing, computer vision, machine learning, and efficient code, who is an accomplished hands-on developer. Now, many people are good at designing and implementing technology, like Pete. Some people are good at thinking about the big picture of where technology is going. It's very rare, though, to find a single person who's good at both of those things, and Pete is one of those people. He's not only a first-rate developer, but also a big picture thinker. He's someone who regularly writes code for tools and applications, but also somebody who regularly provides, I think, important insights on where the technology is heading, where it needs to head, and why. I encourage you to follow his blog as one great source for those insights. And he's also someone who's having an enormous impact on our field through his work on the TensorFlow framework and related technologies and applications and in the industry ecosystem. Pete's work in visual computing began in 2003 when he created a set of image processing filters for detecting features in video content that ran at 30 frames per second on 2003-era laptops. Pretty remarkable. Other people thought so too. Apple bought his technology and hired him. Later in 2011, Pete co-founded Jetpack, where he served as CTO and built the company's technical team. This was a venture-backed startup that created a really interesting product that analyzed hundreds of millions of photographs from Instagram and turned them into in-depth guides for more than 5,000 cities around the world. Jetpack was acquired by Google in 2014, and Pete joined Google at that time. At Google, Pete is currently a staff research engineer focused on enabling the deployment of machine learning in cost and power-constrained systems. He leads the development of the TensorFlow Lite machine learning framework for mobile and embedded applications, including the recently released experimental version of TensorFlow Lite for microcontrollers, which is really remarkable. It can be used on tiny microcontrollers with less than 100 kbytes of memory. We're used to thinking hundreds of megabytes of memory, of course, are required for deep learning. Not necessarily so, says Pete. While much of Pete's day-to-day work is focused on TensorFlow, today I've asked him to share some of his very interesting big picture thinking on where embedded machine learning is headed and why. Please join me in welcoming Pete Warden.
Thank you, Jeff. So Jeff is too kind, though he did on a recent call accuse me of being a thought leader, which I took great offense at. That's, that doesn't seem like a real thing. But yeah, we've been talking a lot about what's happening in embedded vision and in deep learning generally. I'm very grateful to Jeff for the continued opportunities to come and talk to such an amazing audience that he's gathered. As I'm going through my talk, I'm actually going to be pointing out a few key collaborations that actually came about because of Embedded Vision Summit and especially Embedded Vision Alliance quarterly meetings, where I was able to connect with engineers from, awesome, thank you. Just go to present. Well, I was able to connect with engineers from key companies like Qualcomm, for example, and begin collaborations that really made a difference. So I'm very, very excited to be here today. And what I'm going to be talking about is a pretty big idea, like the future of machine learning and computer vision and why it's tiny, why we're investing in these microcontroller solutions, why we're looking at tens of kilobytes as some of our requirements. And let's see. Oh, I need to plug in one more USB, and then this should work. Okay, let's see. We have, yes, We have a joke at Google that we may be on the way to solving AI, but AV is going to be well out of our reach for many years. So to tell you this story of why tiny embedded machine learning is important, I actually want to go back in time a bit and start with a message that may be starting to seem very familiar now. And it's the fact that machine learning, and especially deep learning, is actually useful. It really works. Computer vision is obviously something that's dear to everyone's hearts in this room. And we've seen that even in commercial applications, deep learning networks are starting to become the majority of practitioners are using them. Voice interfaces are using them heavily. But just to sort of back this up a bit, machine learning, particularly on phones, particularly on the devices that we have in our pockets, is a massive deal. TensorFlow Lite alone has over 2 billion mobile devices using deep learning in production. There's all sorts of examples like Google Assistant and the keyboard transcription. A big part of Google I/O a couple of weeks ago was talking about the ways that we've actually got these neural networks that are running at full server quality, running locally on these phone devices. And with my Pixel phone, when I actually leave it out on the table, it will be listening out for music, for example, and it will show me on my lock screen any music it's identifying, again, using a neural network. The billboards you may have seen comparing the Pixel photo performance against certain other manufacturers, they're using computer vision neural networks to help the camera photo quality. Live captions, actually being able to get sort of closed captions on any audio that's playing on your phone, even if you don't have a connection, is using local neural networks. Even the battery management for Android phones now uses neural networks to actually control the scheduling of programs. So something that's super low level that you wouldn't even think necessarily of using a neural network for, it's actually proved to be the best solution. So just to bring this home, here are just some of the applications that are using TensorFlow Lite on mobile devices, both within Google and externally. And what that has meant is that phone processor manufacturers, people who build the hardware for running these phones, have actually offered a lot of support, both from new hardware and from the software layer. So things like Qualcomm HVX, which is a DSP, which is in all Qualcomm phones. And that's actually one of the things that came out of an Embedded Vision Alliance meeting when I was standing up on stage a few years ago and saying, hey, I want a bunch of 8-bit multiply ads. That's all I need to run my neural networks, pretty much. And the Qualcomm DSP engineers in the audience were like, oh, we've already got a part that does that, and it's in a lot of phones already. So we've been able to have a lot of investment from people like Qualcomm, from people like ARM in their neural network library. And the reason that they're actually investing in this is because there's consumer demand for the features that this enables. They're not doing it out of speculation. They're not doing it out of some sort of hope for the future. They see practical demand. They see that this is really needed. And some of this may seem familiar, hopefully, because back in 2017, this was pretty much my pitch. What I was talking about over the last few slides, I was trying to push the idea that this change was coming, that running all of these neural networks on phones was not going to be a fad, it was not going to be a fashion, it was not going to be some kind of airy-fairy research idea. It was going to be a crucial part of everyday application developers' work, and we needed to get up to speed ourselves, we needed to build support for it, we needed to be looking at it as we're building applications. And really that any program that's doing anything that's got kind of the complex heuristics and rules that you're sort of having to kind of struggle with as a programmer that aren't completely obvious, you can actually often benefit from machine learning. And that doing this on device, in that case on a mobile phone at that time, was super important because you get interactivity. It's a lot cheaper from an energy perspective to run networks locally rather than having to transmit data up to the cloud and getting it back. And obviously, you're keeping all of this data locally on the phone. And these have, by and large, all proven to be true, as we've shown. And the reason I'm pushing this is not to sort of try and claim some role as a thought leader or anything like that, because I really hate that framing, but because I'm in a position where we have a lot of developers, literally hundreds of teams inside and outside Google who are developing products, coming to us and saying, hey, can we do this? They're giving us their requirements that are not being met. And that gives us a unique insight into what needs to be built, like what is coming down the pipe. Because I hate saying, no, you can't do that to these people, because they often have really interesting, really impactful products that they want to build. So I see a big part of my role as gathering together a lot of these requirements and then trying to pass them along to people like this audience who have a lot of power to actually make changes and to actually build things and to have an impact themselves. So I'm not any kind of prophet here. I just see a lot of machine learning applications. And I want you to bear that in mind when I jump into what I'm doing in my next section, which is looking forward to what's coming over the next couple of years. And as you might have guessed from the talk title, this is about running neural networks on even tinier devices than phones. So running machine learning, and especially deep learning, on these embedded devices that might only have tens of kilobytes of ROM and RAM memory. And to answer the question of why this is going to be important, I need to paint the larger picture of why we're getting so many product requests, why running machine learning on these devices is so important to so many people who are trying to build really impactful, interesting things. So coming back to one of the examples I talked about earlier, it still blows my mind that it's possible to do full server quality, like the best production systems that we can build within Google, we can match them running on a phone locally in real time. And with a model that's only about 80 megabytes in size. So this is doing full automatic speech recognition the best way we can, and it actually runs in a comparatively small model, and it runs on an ARM A-series chip that you get inside sort of a typical Pixel phone. Now, one of the things to think about here is that this is not a million miles away from being able to run on an embedded device. If you think about the model sizes, you could definitely see over the next few years embedded devices being able to get into the tens of megabytes of model storage. And as I'm going to talk about in some later slides, I'm really expecting that the processor computing power is going to increase so that models that are only able to run on kind of an ARM A series right now should be able to run on something that's kind of more of the class of a ARM Cortex-M or that sort of power regime. And why is that important? Well, think about having a 50-cent embedded chip that's able to run on a coin battery for a year or plug into another circuit and draw almost no current, that can do full, high-quality automatic speech recognition. In terms of the impact on voice interfaces, having voice interfaces on anything you can imagine, having voice interfaces be as cheap and as easy as adding a switch or a button to a consumer device, I think is going to be a massive change over the next few years. And why am I talking about this at a Vision event? Because vision is actually going to be key even to these voice interfaces. One of the things I really want to do personally is just be able to, especially if I have dozens of different devices that respond to voice commands, I want to be able to just look at a device and have it know that I'm talking to it, just like I can do that as I'm chatting to people in a room. That's a very natural interface. I want it to be able to recognize body language and gestures. And even just with pure voice, there's a whole bunch of things that having vision sensors can actually make much more powerful. And I'm going to show a quick video on this next slide. And what this is showing is it's being recorded with a single mic. It's a YouTube video of two people talking over each other. And using a combined vision and audio neural network, you're able to separate out the audio channels of each speaker just using the visual information. So I'm going to hit play on this audio, and hopefully it should start off hearing two people talking, and then it will swipe between each individual channel that has been picked out purely by the neural network with no other sort of audio processing. Oh.
I'm not a fan of flying. I hate it. Hate being on planes.
He might say,
in general,
my
there's so many
stripes
noises.
are solid.
You know what I mean? I won't flush the
And I'd
toilet
say,
on an
oh,
airplane because of the noise. Like, it scares me. You go, you hit flush, then you turn around, nothing happens for 5 seconds. Then out of nowhere, boom! Boom! Oh my God! I just put a hole in the plane.
The city bus does not terrify. It is like a little UN meeting on wheels every time you get on it. We all walk through the same door. We all pay the same price.
So you can see those aren't quiet people. And they're both talking over each other. But by using information from looking at how they're talking, it's actually possible to tell who is talking and separate out the audio in a way that's going to be extremely useful for voice interfaces. So other places where I think embedded microcontrollers are going to have a massive impact, if you think about things like predictive maintenance and the idea of being able to sort of peel and stick a sensor and stick it onto a motor or a piece of machinery, and having that sensor have accelerometers, microphones, and cameras, that can be very powerful. If you think about the accelerometer, you know, how is the machine shaking? Is something changed that's indicating a problem? If you think about the audio, I think we all know from driving our cars, you start to hear very quickly if something is off with the engine, just from the sound it's making. We should be able to create machine learning models to kind of replicate that for all kinds of machinery. And on the vision side, there's a whole bunch of conditions that you can tell just by looking at an image. Like, is there liquid coming out of this when you don't expect liquid to be coming out of this? Is there smoke? Is there rust? Is there some other kind of corrosion? Like, what's happening with the machine? We should be able to use sensors to, especially image sensors, to capture a lot of that information that we can't easily capture now. And you might be asking, okay, these are machines, surely they have power. And they do, but surprisingly, as I've worked with people who are dealing with this environment, it's incredibly hard often to get mains power to devices on a factory floor, because it can cost thousands of dollars. It can be extremely hard to get something wired in. So having something that you can just peel and stick, and that is an independent embedded device using very low power, is very important. One of the key vision applications that I get a lot of requests for is, hey, is there a person nearby? Can you have an image sensor that you can use to wake up a device or wake up an interface when there's someone actually nearby who might want to interact with something? And this applies to a lot of different systems, but one of my dreams is to actually be able to shut down streetlights when there's no people, bikes, or cars around. Because whenever I'm flying over the country, you see this beautiful kind of gossamer threads of lights everywhere. And especially if you're taking a red-eye flight, you know at 3 a.m., most of those lights are just lighting up wildlife and washing out the sky and using up extra power that we don't need. So I don't know how practical this is, but I would love to see if we could actually have streetlights that are only on when people are nearby. One of the use cases that comes up a lot is actually trying to help us grow the food that we eat and grow it in a more sustainable and environmentally friendly way. And there's a lot of machine learning models out there that can use vision sensors to monitor crop health, to understand if there are pests around, to actually help us apply chemicals or do other work much more sparingly and much smarter. And if we can actually get these models deployed throughout fields using tiny cameras that don't need any kind of mains connection, that gets really interesting. And I'm going to talk about a couple of examples in the agricultural space that aren't quite on embedded yet, but show that machine learning models could be really useful for this. This example is actually using old Android phones that are solar powered, that are put up in trees in the Amazon rainforest to actually help detect the sound of chainsaws and try and give early warning when there's illegal logging happening so that the local people can actually help protect the rainforest that they rely on. And I'm going to play another quick video here, which is actually showing how using vision can actually help with crop diseases.
Cassava is a really important crop. It provides for over 500 million Africans every day.
Cassava is a good source of nutrients. It can withstand harsh conditions, and because of that, a lot of people are farming it. There are several diseases that affect cassava, and they make the roots unedible.
And these diseases are reducing the cassava crops by between 40 and at 100%. So we're trying to use machine learning to respond to those diseases.
The app that we've designed can diagnose multiple diseases. You wave your phone over a specific leaf, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, you learn about the best management practices. We're in a very rural location. People don't have access to internet, and TensorFlow is the only platform out there that can allow us to build these advanced models, but deploy them onto a phone.
Because out in the field, we need to give the farmers the access to the information immediately.
So with AI tools and machine learning, you can grow more crops, you can protect them, and you can have a much more reliable source of food.
AI offers the prospect to fundamentally transform the life of hundreds of millions of farms around the world.
You can see a product that can actually make someone's life better. This is kind of revolutionary.
And so that is another example of a machine learning algorithm that's running on a phone. But think about if you can actually shrink that down and running on a device that can be out in the field continuously, or maybe hundreds of devices in a field, then it can get really, really interesting. So one more use case that I want to talk about is medical devices. So actually trying to understand what's going on with our bodies and looking at things, everything from heartbeat to insulin to exercise. And one question that Jeff had when I was talking about this with him was, okay, well, why can't you just use existing sensors for some of these measures? Image sensors especially can be far more powerful in understanding what people are actually doing, not just measuring steps, but measuring how people are moving, how much energy they're using. And then if you think about if we can actually miniaturize these enough to actually look at the insides of our bodies, being able to swallow or be injected with something that's a tiny image sensor that's able to look at what's going on and actually make intelligent judgments and report back, I think that that could be incredibly powerful. So what do we need to enable these tiny machine learning, these tiny sort of devices that can have such a big impact? The number one issue we face is energy usage. I was talking with Jeff about this as well, and he brought up cost as a big limiting factor, but I have the optimistic view that as these things become useful enough, the volumes will grow and the costs will drop. What is a lot harder to deal with is the physics of energy. And why is energy such an issue? It boils down to the fact that mains power is not available in almost everywhere where we want to have these sensors. And even where there is mains power, like I talked about the factory use case, it can be very, very hard to actually connect new devices to that mains power. It just may be impractical, it may cost a lot. So what we're left with is the idea of, okay, we need something that runs on batteries, or we need something that runs on energy harvesting. If you're looking at something that runs on batteries, if people have to recharge those things, we just about are able to, or at least I'm just about able to remember to recharge my phone every night. Once we get up to dozens or even hundreds of embedded devices per person, then the burden, the tax of actually having to deal with replacing batteries, even replacing smoke alarm batteries is enough of a pain. If you imagine our entire lives could just be spent trying to replace batteries or trying to recharge devices, if we have to keep doing that at any regular interval. So we don't want to become kind of bound the devices will not scale if we have to pay a tax, if we become bound to charging or changing batteries. And it's really a complete sort of phase change, the idea of going from something that has to have its battery changed, even at, every few weeks, to something that you never have to change the batteries on, that you can actually just put somewhere and it will keep working and you can forget about it. So having these peel and stick kind of devices is really the only scalable way that we're going to be able to expand the number of smart sensors that we have in our world. And there's actually some existing work around smart sensors for very simple linear things that you can measure, like temperature, like lighting values, like humidity, that the Department of Energy has been sponsoring. But you really need machine learning to get beyond those very, very simple kinds of sensors. And what this actually boils down to in practice is, for these devices, you need batteries that last years, or even better, you need energy harvesting, so you don't even have to worry about the lifetime of the batteries. It's effectively infinite. And what this boils down to in practice is to reach these goals of never having to change batteries or being able to rely on energy harvesting in any kind of reasonable sized package and any kind of reasonable cost. You need something that's less than a milliwatt continuous power usage. So we have this kind of regime of extremely low power. Mobile phones are around a watt if they're pretty active. So we're looking at sort of 1,000th of the energy cost of something like a mobile phone. And how do we get there? One of the big challenges is that radio is really, really expensive. Sending bits from one place to another, it turns out, is extremely hard to do without spending a comparatively large amount of energy. Even things like Bluetooth Low Energy are still using high tens of milliwatts, and things like cell data transmission or Wi-Fi can easily use hundreds of milliwatts to send data. And those numbers don't seem to be getting dramatically better. Things like bandwidth are improving a lot with 5G, but if anything, the energy used to send that much faster data is actually growing as well. So if we're working in this 1 milliwatt kind of regime, there's no chance that we're going to be able to send data continuously from our sensors to the cloud to be processed. There is some good news, though. The sensors themselves require very little power. Microphones you can get off the shelf can work in small fractions of a milliwatt. We've actually had some success over the last few months working with some companies like Himax and Pixar who create image sensors that are actually able to run below 1 milliwatt. They're only like 320 by 320, black and white. But having commercial sensors that can actually operate in this regime is really important and really encouraging. And looking forward, there's been some really interesting research about image sensors that can power themselves through incidental light. So there isn't any theoretical reason why we can't have very low power sensor parts of our system. What this means at the moment is kind of like the graph that Jeff was showing earlier about the amount of data that's being captured by image sensors. Almost none of that is being used. We're dropping all of this data on the floor because we can't afford to transmit it anywhere, to have something useful done with it in kind of a server context. So it's just being completely ignored. Whatever valuable information in there is being lost. One of the other pieces of good news is that microprocessors can be very energy efficient. We've been working with Ambic. We have the SparkFun Edge board that we've collaborated on that is a small $15 board you can buy that draws about, I think, 1 or 2 milliwatts of power to run a voice recognition example. And there are a whole bunch of other really innovative, impressive startups out there that are putting together very low power processing sensors. And there's really no fundamental reason why we can't do the kind of computation we need to do in microwatts, in much less than a milliwatt. Because one of the nice properties of these neural networks is they require a lot of arithmetic, but they don't require a lot of loads and stores to and from memory. And I'm not a hardware person, but from talking to the hardware designers I know, they're very excited by that ratio because doing arithmetic can be done locally on registers can be done very, very cheaply from an energy point of view, much more so than sort of loading or storing to any kind of memory. So if you bring all this together, having low power sensors plus low power compute means that we are able to run deep learning models on these devices. And these models can actually make sense of all of this data or a lot of this data that's coming in. And what that means is we only have to wake up the radio when something important happens. Like, sort of once a day when there's, somebody where they shouldn't be, or where there's, a funny noise coming from the motor, or there's liquid spilled on the floor. So the energy costs of radio become much, much less important because you're only waking up for a few seconds a day, so you can afford to power it through batteries or through energy harvesting. And the point of this talk is we actually need your help to make this happen. As I said, I'm genuinely very excited to talk to this audience because it's full of people who are actually building real products, who are facing real problems out in the world and trying to solve problems that can have a really big impact if we're actually able to address them. So on a practical level, I'm looking forward to talking to people from the audience who actually have products that you look at these emerging capacities that are starting to develop, and you say, oh, that would actually really help us. If we could package what we're doing down into a kind of thing that you never have to change the batteries for, that's cheap, that you can just kind of peel and stick, that will be really, really useful for us. And the reason that I'm so interested in that is we're still in the stage where the parts of this puzzle are coming together. And in order to drive adoption, and in order to help sort of push forward what's happening here, we need to move beyond the experimental stage, and we need to have more practical examples that we can point the rest of the world to show, hey, this is a real thing. And because we know it's still pretty early days, especially if you're trying to run machine learning models on something that only has 20 kilobytes of RAM, we're happy as the TensorFlow team to kind of offer advice where we can and try and sort of help people actually get started down this road because we think that it's really important. So that's the number one takeaway that I want you to leave with is my email address is petewarden@google.com. Feel free to drop me an email. I would love to hear from you. I will be hanging around afterwards. We should talk about how we can actually turn some of these ideas that are floating around that we believe are now possible into reality. Another ask for this audience, I know there's a bunch of people who are involved in hardware out here. One thing I found really interesting is it was super hard to find any embedded development boards with microphones built in, because there wasn't that much you could do with a microphone on a microcontroller before there was some kind of machine learning model to interpret it. You could sort of, recognize sound levels, but there wasn't that much more interesting you could do. And there definitely wasn't anything you could do with image sensors, because, what are you going to do with a video frame on a microcontroller? You can't afford to transmit it anywhere. So we encountered this problem where we actually had to kind of sponsor the development of embedded development boards that had these sensors built in. And we're keen to keep pushing forward that work. So anybody who's actually working on the sensor side, who's able to offer sensors that might actually fit into this world, we'd be very interested in talking to. Talking of sensors, we also love having more development boards that we can run TensorFlow Lite Micro on and actually push forward the choices that our users have for running these sort of things. And the framework itself, we've tried to make it pretty portable across a wide range of architectures, but we really want to be able to point our users at boards that they can build simple machine learning sensor applications on. So, come and talk to me about ideas for your hardware that you want to see out there in the world being used by people to prototype these products. And looking forward, I really want to leave you with this idea that there's an incredibly big world of embedded devices out there already. 250 billion is kind of the best estimate we have of how many active devices there are. The number of devices shipped every year seems to be growing by 20% without much sign of that slowing down. And to contrast that, smartphone sales are pretty much roughly flat. The number of new internet users is growing in kind of the low single digits, largely because we've been so successful at reaching so many people. So this is an incredibly exciting market that's happening. And it's giving us the opportunity to solve a whole bunch of problems that we've really struggled to solve in the real world, out there in the physical world where our mains power just won't reach. So I'm really excited to do what I can to help us actually develop these products. And I'm really hoping that you'll be able to push this forward too.
Thank you very much, Pete, for that really insightful presentation, leading us into the future, but not thought leadership.
No, never.
Definitely not. We'll have time for some Q&A. If you have questions for Pete, please approach one of the microphones in these two center aisles. And in the meantime, I'm going to start, Pete, with a couple of questions. Maybe I'll start from towards the end of your presentation and work my way back. You said about being able to optimize these systems that they're mostly compute, there's not so much need for loads and stores. And that's a little counterintuitive to me because I'm used to thinking, well, we're streaming video through a system. It's a lot of data. We've got models that are big. Some are bigger than others, but the models have lots of parameters. So there's lots of data, coefficients and video data that needs to be processed. Are you saying that, are you making a distinction between streaming data and sort of retained data? Or what do you mean?
So really what I mean there, and I actually come from a background dealing with sort of streaming video and 60 frames per second, like HD video. The amount of computation that's involved in a typical neural network can easily be many billions of operations per frame. And typically, they're working on comparatively low-res inputs, like 300 by 300 RGB inputs, even if they're operating at a high frame rate. And their models, even though they may be tens of megabytes, that number of parameters pales in comparison with the tens of billions of operations, arithmetic operations, that may be happening to actually execute that model. So even though the input and the model size parameters may seem big, what you don't see kind of under the hood is how massive the number of operations being done on those are.
Okay, so you're basically talking about the ratio of compute to memory operations.
Yeah.
So yeah, memory, there's plenty of memory, but the compute's so big that it sort of swamps the memory. Got it. Question over here.
Hi. Thanks for the presentation. It's fascinating and inspiring as usual. So, and my question is about, you presented as well machine learning on these very low power devices. Although what's happening here in most of the cases is machine inference on these low power devices.
Yes.
So do you see a role for actually learning and training, which typically happens somewhere else, on these very low power devices? And if so, how and why?
No, that's an awesome question. And it's something that comes up quite a lot. And I see a few different aspects to this. One of them is that there's this really big continuum of training. One of the things I actually want to be able to do to extend the the speech recognition wake word example that we have as part of TensorFlow Lite Micro is do a very simple top layer retraining on device so that a kid, for example, can name their toy, give their toy a name, say it 3 times, and then it will actually be able to respond to that name. And I'm working on doing that just by leaving the whole network as it is, but kind of doing an embedding at the end where I do k-nearest neighbor to kind of look up. And that's a kind of a very simple kind of training. And it's very similar to what happens at the moment when you get your phone and you sort of give it you train it a few times with the wake word so that it kind of recognizes your voice better. So I'm expecting that is going to be very common on embedded devices. Now, then, once you get into, can we do full retraining on these devices? I am expecting that will be coming along kind of later than the kind of all of this inference stuff that I'm talking about. I do see that there's going to be a role for that, but there's still a lot of practical questions. Like one of the things that always scares me about putting these models out into the wild and letting them retrain is you never know how they're going to retrain themselves. It's like there's a whole like QA process we're going to have to think about keeping these models within kind of acceptable bounds. And yeah, so even beyond the technical questions of how do you do like the retraining on the math side, there's a whole bunch of like product design questions that I'm a bit scared by.
That'd be like when I put my cell phone through the washer last week. It came out still working, but imagine if it had retrained itself.
Yes.
Yes, sir.
Yeah, thank you for a great talk. You listed a number of very nice applications for this. I'm wondering if you have thought about potential dangers or abuses of this technology, like what happened with facial recognition in China. Do you think as engineers our main focus should be in enabling these technologies, or and it's up to the society to figure out later, or are there things that we could do at this time?
I do think we have a big responsibility as we're pushing this technology forward. One of the things that I'm very keen on is actually making sure that we have a very open discussion, and that we start talking about what's going to be possible before it's possible, so that we have the chance to have kind of the whole of society understanding kind of what's coming and having a chance to help shape it. There's also some very practical considerations. Like, one thing I haven't talked about is I really don't want to be generating a massive amount of smart litter, because you know, these things might have a 5 or 10 year lifetime, and then you know, if they're like out in fields and they're never picked up, like we're suddenly creating this massive trash problem, and that sort of keeps me awake at night. So I think we need to be as engineers, we have a big responsibility to be kind of looking at the potential issues, trying to highlight them, trying to figure out solutions as we're kind of building the initial versions of these. So yeah, I'd love to hear your, afterwards we can hear your thoughts about what we can do there.
Thank you.
Thanks.
Yes, sir.
Yeah, great talk, thank you. I've been in the IoT, microcontroller, radio space, now Foundry for most of my career. I think the technology's here. As a comment, what you showed is great. There's many other presentations at Foundry level, microcontroller level showing the same. I think a major impediment to adoption is the business model. How can you share the cost, margin sharing? I have some thoughts on that, but maybe that's a longer question. Your thoughts on that?
Well, I'm hoping, I have to admit, my business, I joined, as an example, I joined Apple in 2003, and my biggest fear then was that they were going to go bust. So my business acumen is is not well renowned. One of the things I'm hoping is that, Google has this incentive. We want to build products around this hardware, which is one of the big reasons why we're trying to give away the software and give away the examples, and kind of at least see if we can kind of jumpstart and help where we can to get demos off the ground. One of the big challenges with the IoT space is that it is largely based around things like subscriptions right now, and that may make it harder to do things where the device is off doing its local compute, because then it's kind of harder to tie back into kind of a subscription model. So I see a lot of challenges around the business model, but I guess I'm hoping we'll make it up on volume.
Yes.
Pete, so one thing you talked about today was mostly centered around a single microcontroller sort of take. And I'm really curious to see, once we solve the problems about the single microcontroller, how would you look at it when you have a whole bunch of them?
Yeah, and I guess one of the things I'm hoping for there is that as we're able to understand things like audio, and even maybe have visual signals from these microcontrollers, that there are going to be ways that we can use those human understandable interfaces to have microcontrollers talk to each other. I mean, and possibly even literally talk to each other, because there's, this is probably maybe too wacky an idea to be real, but I love the idea of your smoke alarm saying, there's a fire, and then your toaster saying, oh no, it's okay. It's just I'm just burning toast, but not having to use some proprietary, and just talking to each other, and you can kind of overhear that and be like, oh, okay, everything's. So that's as far as I've thought it through.
That's a practical problem.
Yes.
Question over here.
Thank you for the talk. I have a question about the hardware platforms. You give some examples of low milliwatt level sensor board or with a microprocessor, but I know that Google has a HTPU solution. Why it's not mentioned there, and whether that's targeted for maybe a more narrow application field, or you're trying to cover more universally?
No, that's a great question. The edge TPU is somewhere in the order of 500 milliwatts. So it's an awesome accelerator, but in terms of being able to run in the applications that I'm really interested in this like sub 1 milliwatt range, it's kind of, it's very efficient, but it's also, comparatively high power total usage. So that's why I haven't really sort of covered that in this talk.
Have you explored the applications in the 500 milliwatt range? Was there any limitations like latency? You have to have batch 16, 32 to do that job, or your application is batch 1 or batch 2?
So what I see with a lot of these sensor applications is that they're almost always batch 1 because you want that latency. Really what I'm focused on and what I care about is, hey, how can we operate these very small batch, low latency kind of applications? So that's where I've been focused.
Thank you.
Thank you.
So maybe one last question, Pete, before we wrap up. You said 1 milliwatt. 1 milliwatt, I think you're referring to system power.
Yes.
We're really down now to a system that can operate on ambient light, sensor, processor, the very low duty cycle radio, and so on. Sounds a little nuts from where we are today, right? But from your perspective, you're in touch with a lot of the leading edge of commercial technologies. When do you think we'll be there? When do you think we'll be at a 1 milliwatt system that we can ship in commercial volumes that's doing, maybe it's not 30 frames per second HD video, but it's doing the kinds of things that you've been talking about?
So with that SparkFun Edge board that I was pointing to, I think with the LEDs flashing, we've measured it at like 2-point-something milliwatts. So it's not a crazy idea. And that's running the speech recognition neural network model, which is actually a small image recognition model running on a spectrogram that's derived from the audio data. Mm-hmm. So we're like, and that's with a fairly standard like Cortex M4 that just happens to be using Ambic's low voltage technology. I actually just got sent some new numbers from Sentient just this morning, who are one of the startups I mentioned, who they're running the same application in like the low hundreds of milliwatts on complete system power.
Did you mean microwatts?
Oh yeah, microwatts. Yeah, milliwatts would not be impressive.
That's great. So basically what you're saying is it's just down to the LED guys now. We need to get them. Excellent. Well, Pete, thank you very much for a really, really interesting presentation. Thank you.
Thank you, Jeff, and thank you, everyone.